Hey everyone, welcome back. Mandar Chakrabarti here. Hope you all are doing good. So we were just having a discussion about the del operator, and till now we have understood what is the mathematics behind the del operator, what it actually does, and we have also understood what is the basic intuition behind such an operator. Now in this video we actually want to dive into some of the application areas of this particular del operator. If you are joining us for the first time, and if you are interested in the world of wireless communication systems and how it all functions, and in the world of electromagnetic field theory, then I would request you to subscribe to the channel. Basically, the del operator that we were discussing, we have applied the del operator in the earlier video on a one-dimensional function. So the function was only a y equals to x square. So it was a function of only one variable. Now this time we want to increase on that. We actually want to go into a two-dimensional situation, because electromagnetic field theory deals with three-dimensional situations. So slowly we want to get into that area. So let's check that out. So the vector differential operator, if I want to apply it now on a two-dimensional situation, the image something like this. So a function something like this. Now this function over here, this is a scalar function, okay, and mathematically this function is represented by f of, well, this time it's going to be x and y, and that is equals to x square plus y square. So in the earlier video we had done the function y is equals to x square, and we had found out the derivative of that function, and we had done that by taking 2 points on the x-axis, finding out their equivalent values on the y-axis, and then calculating the difference between them, and that was the general process in which we went about it. So same thing, same logic we are going to apply for this one as well. That is the reason why I wanted you to recollect the graphical process of calculation of derivative of any sort of a function. Since now I am dealing with a two-dimensional function, and mind you, this is a two-dimensional scalar function, not a vector function. There is no direction associated with this. Okay, so since we are dealing with a two-dimensional function, so basically what you can see is this surface. Let me mark that out for you. So this entire surface, this is the xy plane, right? And this axis over here, this is the z-axis. So essentially I am now having a three-dimensional, like the way that I had shown you, a three-dimensional region. Earlier one we had taken 2 points on the x-axis. So this time our first step is going to be taking 2 points on the xy plane. Let's take them. So suppose I take 1 point over here, and let me bring that up to the curve. So if I bring that up to the curve, it will come somewhere around, say, here. Now this time let me take another point like we had in the earlier one. I'll name these points, okay. So I name this particular point as A. Now the second point that I take, I'll take somewhere this time here. Let me bring that up, and that one goes all the way, say, somewhere over here on the graph. Now, so earlier one we had actually moved along the x-axis. This time we are not exactly moving along the x-axis, but rather we are moving along an axis something of this sort, right? So I'm going to call this as a vector. Say I call it as my S vector. Okay. And so this time, the earlier one, we were finding out basically df dx. This time what we are actually trying to calculate is df ds. Alright. So I'm going to split this into two parts. What I will do is, first I will travel along this axis. So I'm going to travel along my x-axis. If I travel along my x-axis, I am keeping the value of y constant. Second one, step 2 is, now I travel along my y-axis. This time I keep x constant. So let me name these points. So this point that I arrived at, I name it as B, and the final point is named as point C. If I am traveling along x-axis keeping y constant, that's the equivalent of a partial differential, right? Just think back to the earlier video. Partial differential is considering one axis, considering one variable, keeping the other variables constant. So x-axis keeping y constant, that's a partial derivative. Y-axis, partial derivative with respect to x. Y-axis, moving along y-axis keeping x constant, so that is a partial derivative with respect to y. Now let me give a little different name to this function of ours. Let me name this as, say, phi. So this function of ours, I am naming it as phi. So what I am trying to actually calculate is d phi ds. Now check out this step. So d phi ds can actually be written as partial derivative of phi with respect to x, right? And then I want to find out how much x is changing with respect to s, and add to that partial derivative of phi with respect to y and how much y is changing with respect to s. Okay. Now, if this were to be a three-dimensional function, right now we have considered that it's a two-dimensional function, but just to make it a generalized expression, let's say that this function is a three-dimensional function. So in that case, I would also have partial derivative of phi with respect to z, and then how much z is changing with respect to s. So since this s vector plays such a very important role, let's check that out with a bit more detail. Let me draw that out for you on a fresh page. So the s vector lies on the xy plane. So this is my x and y plane. This is my this is x-axis. This is y-axis. And this is my s vector. S vector goes from point A to point C. This is my S vector. Since it's a vector, it must have a unit vector. So let's name that unit vector as U. Now I have moved from point A to point C via point B. So let's draw that. This is my point B. Let's give some initial and final coordinates. Initially it was x0 and y0, and finally I have moved to x and y. So what would be the coordinates of point B? That's right, point B is going to be x, y0. I have changed in respect to x, but I have not changed in respect to y. Let's give these some dimensions. Let's call this as Lx and call this as Ly. Now, look a bit more detailed at this unit vector u. Again, x-axis and y-axis. This time, since it's x-axis, it's I vector, in y-axis this is my j vector, and this is my u unit vector. So this u unit vector, let's again consider some values, and this one is bj. So let me write it out for you now. So u vector is ai plus bj. If I were to extend this onto the third axis, then it becomes plus ck. Okay, there is a angle over here for consideration, same angle. Now, one thing that I can write, cos theta is a by u. Okay, check that out. Cos theta is a by u. Now, u has got a magnitude of 1, so that is essentially a. Similarly, your sin theta is b by u. U having a magnitude of 1, so that is equals to b only. Apply the same logic here, and I can write your Lx is s cos theta. So essentially it is s a, and Ly is s sin theta. So essentially that is s b. Okay. Now, from the axis point of view, from the coordinates point of view, your x was x0 plus Lx. So that is x0 plus as, and y was y0 plus Ly. So that means y0 plus bs. Okay, let me go to a fresh page. Now, x is x0 plus as. So then, can you tell me what is going to be dx ds? That's right. Now, x0 is a constant value, so it becomes 0, and differentiating as with respect to s, finally I'll end up with a. Same thing, y is y0 plus bs, and differentiating y with respect to s, I'll end up with b. And if I were to extend this onto the third axis, then z would be z0 plus say cs, and dz ds is going to land up and become c. Initially, we had considered our original function was this one. So, original function, let me write that again for you. The differentiation of phi with respect to s is partial derivative of phi with respect to x, and how much x is changing with respect to s. Partial derivative of phi with respect to y, how much y is changing with respect to s, and partial derivative of phi with respect to z, and how much z is changing with respect to s. Now, if you see the first set of equations, then I can replace this over here, this over here, and this over here, and I get d phi dx a plus d phi dy b plus d phi dz c. This is the result of the differentiation of phi with respect to s. Now, here I have one question for you. Can I write this particular result as the scalar dot product of two vectors? Think about it and you can tell me that yes, I can write this as the scalar dot product of two vectors. Something like this. So, d phi ds is equals to d phi dxi plus d phi dy j plus d phi dz k dotted with dot product of ai bj c k. Okay, and this one that I landed up with over here, this one is nothing but the u vector. Check it out. See, right there, u vector over here. That's the u vector. So, this is now what I get. Now, let me rephrase this particular statement in another way. So, my the derivative of the two-dimensional function with respect to s, I am going to write it as I partial derivative with respect to x plus j partial derivative with respect to y plus k partial derivative with respect to z of this scalar function phi, if I were to take phi common from all these three equations. Okay, I am taking phi common from all these three equations and I am taking them out, and this is what I land up with, dotted with my u vector. And this one that you see, this one over here, this is the del operator, the vector differential operator, right? So, it is the vector differential operator applied on a scalar two-dimensional function dotted with this unit vector. That is the differentiation of that two-dimensional function. What does this mean? Let me give you a little bit more clarity now. A dot product of two vectors can result in a different result. This is the magnitude of this one. This one is known as gradient operation. Gradient operation. Basically, the magnitude of the gradient operation and the magnitude of the unit vector. So, magnitude of unit vector is of course 1, and cos of the angle between the two of them. Okay, that is the result of the derivative of this two-dimensional function. And can you tell me when this would be a maximum value? This would be a maximum value when cos theta is going to be equals to 1. So, if cos theta equals to 1, that means theta equals to 0 degree. So, if theta equals to 0 degree, then the two of them are pointing in the same direction. So, I will write that differentiation of a two-dimensional scalar function is maximum in the direction of gradient of that two-dimensional scalar function. Alright. Conversely, I can also say that a gradient function or the vector differential operator applied on scalar functions points in the direction of steepest ascent, or it points in the direction of maximum rate of change of a multidimensional scalar function. Let me give you now a practical example where this gradient function can be applied. I want you to think about your basic geography lessons. You have gone through something like this. This was the slope of some maps. This is known as a contour map, right? It tells us how steep a particular region is. So this two-dimensional, this one on this bottom over here, this two-dimensional representation of this three-dimensional structure, that is a practical example of a gradient operation. And gradient operation results in a vector which points in the direction of maximum rate of change. So, if my region of consideration is only this much, if my region of consideration is only this little much, then the vectors are going to point in that particular direction. Why? Because this particular point, this point corresponds with this point over here. That is the highest point, the steepest point. So, gradients point in the direction of steepest ascent. So, all the gradient vectors are going to point in that direction. However, if my area of consideration was not just restricted to this little bit, but rather to the entire region. So, if it is restricted to the entire region, then all of them are now going to point to this side, because this point is the actual steepest area. Okay, so that was a practical implementation of your del operator, and this is when a del operator is used on a scalar function. And in the next video, I want to discuss more details with all of you regarding this del operator and how it can be applied to different vector functions now. Okay, so before I leave off for today, I want to show you one small animation which might help you a little bit more to clear your concepts regarding this gradient operation. Okay, so that was it for this one, and if you are interested in the world of electromagnetic field theory, then I would request you to subscribe to the channel. We are right now going through a tutorial on the electromagnetic field theory, and that's it for today. Before I leave off, check this one out.